Here we're going to talk about nucleophilic substitution reactions and epoxides. Recall an epoxide has this three-member ring that contains the oxygen, and it turns out that epoxides have greater reactivity towards nucleophilic reagents compared to that of simple ethers. The enhanced reactivity is due to angle strain. So this means that epoxides react with a variety of nucleophiles. Now, the substitution mechanism is going to depend on whether the reaction is carried out under basic neutral conditions or acidic conditions. Let's take a look at the first case here where we're under basic neutral conditions. In this case, these reactions will be SN2. They will follow the SN2 mechanism. The epoxide can undergo the nucleophilic substitution without first being protonated, again because of the ring strain. All strong nucleophiles can open up the epoxide ring by following the mechanism that I'm going to show you in a moment. Here are some of the common nucleophiles. We have hydroxide ion, we have an alkoxide ion, cyanide, and so on. So these are good nucleophiles for this SN2 reaction. So let's go ahead and take a look here at the steps. So here we have an epoxide, and we have our strong nucleophile, the methoxide ion in solution. So the nucleophile is going to attack the carbon that is less hindered. Again, remember this is SN2. So it'll attack the less sterically hindered carbon, and then of course once the nucleophile attacks, the carbon-oxygen bond will break, electrons will stay with the oxygen. And then we end with an alkoxide ion here. Now, in the second step, what will happen is the alkoxide ion will pick up a proton either from the solvent, or we can add an acid after the reaction in order to protonate this alkoxide ion. So we end up with a product here that has two functional groups. We have the ether and the hydroxyl group here. Again, in these reactions, the nucleophile is going to attack the less substituted carbon, or the less sterically hindered carbon. Also recall that in an SN2 reaction, the ring is going to be opened from the back side. So the nucleophile will attack carbon from the back side. So let's take a look at an example here. What I have here is 1,2-epoxy cyclohexane and react it with our strong nucleophile, methoxide ion. We end up with two products. Notice that the reactant, our epoxide here, is achiral. So it has no chiral center. But notice our products here, we have two chiral centers in the products. So what we have here is a pair of enantiomers. And these are actually the trans 1,2 disubstituted cyclohexanes. And again, each one has two stereogenic centers. And because in this case both carbons were equivalent, we'll end up with a racemic mixture. Recall that when an achiral reactant produces a product with stereogenic centers, the product will either be a racemic mixture or a meso compound. So now we'll take a look at nucleophilic substitution reactions of epoxides in an acidic medium. Now, hydrogen halides, will react with epoxides. Water and alcohols will also react, but an acid has to be added to the mixture. So let's go ahead and take a look at the mechanism here. And we have protonation of the epoxide. And in this case here, we're going to use hydrobromic acid. Okay, so there's protonation of the epoxide. Of course, this bond breaks and the electrons stay with the bromine. And so we end up with the protonated epoxide and the bromide ion. The nucleophile is going to attack carbon. And again, that's a backside attack. And the carbon-oxygen bond will break here. And we end up with this product here. Now, in this case here, we have a symmetrical epoxide, so both carbons are equivalent, okay? And so this is very straightforward as to the product that we're going to get. Notice that we have an OH group on one carbon and the nucleophile, in this case the bromine, bonded to the other carbon. So notice here we had a symmetrical epoxide. All right, so both of these carbons are equivalent. And so we can sum the reaction up. You know, again, the epoxide is protonated, then the nucleophile comes in and attacks the carbon-oxygen bond breaks, and of course we end up with a product here that has both an OH group and the nucleophile, in this case the bromide, bonded to the other carbon. Now, in the case where we have an epoxide that is asymmetrical, and right here we have 2,2-dimethyl oxirane, okay, the situation changes. Now, when we react 2,2-dimethyl oxirane with a nucleophile, so this would be under neutral basic conditions, right? We see that the nucleophile attacks the least substituted carbon, or the less. We see that the nucleophile attacks the less substituted carbon, and this is the product that we end up with. Now, under acidic conditions, and that's this arrow here, here I have methanol and sulfuric acid. The acid is so that the epoxide can be protonated. But anyway, if you look at the product here, notice that the nucleophile attacked the carbon that is most substituted. So that's very different from neutral basic conditions. So let's take a look as to why the more substituted carbon is attacked. Let's start here. Again, we'll use the 2,2-dimethyl oxirane. And in this case, we have hydrobromic acid. And of course, the first step is the protonation of the 2,2-dimethyl oxirane. So let's go ahead and take a look at the transition state here. One of the transition states, we'll call this A. And what happens is the epoxide is so reactive that the carbon-oxygen bond starts to break before the nucleophile attacks. And this results in a partial positive charge on the carbon. Now, the more substituted carbon is able to handle that partial positive charge very well, more so than the less substituted carbon. You can also think of it this way. Think of, we look at this carbon here, it's a tertiary carbon. And remember, a tertiary carbocation is very, very stable. Now, if we look at the other case, here we have the least substituted carbon, okay, and here we see the transition state. We see the bond breaking between the carbon and the oxygen. So then the less substituted carbon develops a partial positive charge, and it can't handle that partial positive charge as well as this tertiary carbon. So when you compare the two transition states, transition state A is much more stable than transition state B. So transition state A, the nucleophile attacks the more substituted carbon, and this here is going to be the major product. For transition state B, when the nucleophile goes to attack the less substituted carbon, this would be the product. And again, this is going to be the minor product. So our major product is the one where the more substituted carbon is attacked by the nucleophile. So for nucleophilic substitution of an epoxide under acidic conditions, we say that the reaction is partially SM1 and partially SN2. It's not a pure SM1 and it's not a pure SN2 reaction. Think about it. In an SN1, the intermediate is a carbocation. But in this case, a carbocation does not fully form, so it's not quite SM1. However, it does produce the same product because the more substituted carbon is attacked by the nucleophile. And we say it's partially SN2 because, well, number one, you have backside attack of the carbon, but number two, the leaving group actually starts to leave before the nucleophile attacks, so it's not a pure SN2. So again, it's partially SM1 and SN2.